Okay, so this is one of the last of the integral material that like has the techniques of integration that we're going to cover in this class. This can be one of the more difficult sections to grasp. Once you've got it, it's not too bad, but early on, I have a feeling there will be a lot of confusion. So I'll try to make a follow-up example with or follow-up video with more examples, but let's just go ahead and get to it. So substitution is basically trying to undo the chain rule. So again, undoing anything is a little bit harder than doing it in the first place. So the way we undo the chain rule is by using u-substitution. All right, it doesn't have to be u, but typically that's what we use. All right, so example 1a. Now one of the things that you'll notice is basically our choices, or the setup of the problem and everything will be very, very similar between all the part A's and all the part B's, and look for the similarities between A and B in each of these as well. So hopefully you'll start to see a pattern by the time we get through 3 of these examples, or 6 of them if you will. All right, so looking at this, the whole idea is we want to get this down to one of those formulas, integration formulas that we know. So for instance, we want to get this down to, say, perhaps e to the u du, because I know the antiderivative of e to the u is e to the u plus c. So that's our goal, is we want to get it to look like that. Well, how we do that is we need to look for something that we're going to use for a substitution. And when we choose our substitution, we want the derivative of that substitution to appear somewhere else. All right? So keeping in mind that what our goal is to get to e to the u, you might say, well, if we let u equal x squared, that might get us the trick. And indeed, in this case, it does. But it's not just enough to get that to e to u. We need certain things to happen. We need to deal with that 2x. So let's just see what happens. So if we let u equal x squared, then the derivative of u, I know it seems weird, we're finding the antiderivative, why are we taking the derivative, but just bear with me for a second. The derivative of u is going to be 2x. Now, I'm going to explain this a little bit differently than the book. I kind of like the way this does it. So let's multiply both sides by dx. So I get d equals 2x dx. And finally, this is the step they don't usually do in the book. I like to solve for dx. The reason why I like to do that is because it kind of makes the next step a little bit more brainless. You don't really have to recognize anything. You plug it in and simplify, and away you go. All right, so we made our choice of u, and then we figured out what dx has to be. Because what we're going to do is we're going to convert all these x's that we have here. We're going to basically try and rewrite those, get rid of those, and so we have everything written in terms of u. So with that in mind, let's copy this down. I've got 2x. Now e to the x squared, well, x squared is equal to u. So I'm just going to write e to the u. dx, we said, was equal to du over 2x. So let's write du over 2x. Well, notice something nice happens here. 2x and 2x cancel, and so I get equals integral of e to the u du. Oh, well, that's what we wanted. What's the antiderivative of e to the u? It's e to the u plus c. Finally, we substitute back in, if u equals x squared, we're going to have e to the x squared plus c, and that is our answer for this one. All right, so let's look at this one over here. We got, again, these look very different as far as what we have here, but I want you to, by the end, I want you to see how similar these problems are. So again, I've got something times e to the something dx. Now, one of the things to look for when I'm making my choice for u is I want the derivative of u to appear somewhere else. So I'm looking for, basically, I'm looking for something and its derivative that appears somewhere else. So notice if I let u equal sine of x, the derivative of sine of x is cosine of x. So if I let u be that guy, the derivative of it appears right there. And that's usually a benefit. And the derivative doesn't have to match exactly. Like if I had a 2 cosine of x or something like that, that'd be fine, and we could still make it work. But the key is the x part has to match. So the derivative of sine of x is cosine of x. If I have that match out, then I'm golden. So let's continue on. So I got my u equals sine of x. That's an important part. Now we're going to take the derivative of that. So du dx equals cosine of x, right? That's the derivative of sine of x. I didn't write that because of that. Once I pick my u, I'm just going through and taking the derivative. It's what I do want to happen is I do want them to match, but I don't get to make them match. It just happens to match because of what I picked for my u. So I take the derivative of u, which is cosine. I solve for dx, so I get cosine of x dx, and then I'm going to divide by cosine of x, so I get dx equals du over cosine of x. And now I'm going to make these substitutions. I'm going to replace sine of x with u, so I get e to the u. I'm going to replace dx by du over cosine of x. So, again, notice what happens. Cosine of x, cosine of x. So I end up with integral of e to the u du. What do you know? It's exactly the same thing I got to this last time. What's the antiderivative of e to the u? Well, it's e to the u plus c. And finally, I didn't have any u's to start with, so let's substitute back in. U is equal to sine of x, so I get e to the sine of x plus c. If you want to, you could check. You could come over here and check by taking the derivative. So take the derivative of e to the sine of x plus c. Well, the derivative of c is 0, so that goes away. So the derivative of e to the sine of x is e to the sine of x. Then use the chain rule times the derivative of what's inside. You get times cosine of x. Is that what I started with? Yes, indeed it is. So we've got our right answer. So the hard part early on is making your choice of u. A lot of times if I give you what your u is, you don't have too much trouble. Well, your first homework is 5.5a is actually they give you what u is, and then you just have to go through the process. After that, you got to start picking your own u's. But a big hint to look for is looking for a function that's derivative appears somewhere else. So the derivative of x squared is 2x. Again, if this is a 3x or 4x, it wouldn't really matter. The derivative of 2x has an x in it, so I want this thing to have an x in it. I just happen to pick it, so it's exactly perfect. If this 2x wasn't there, actually, if it was just integral of e to the x, e to the x squared dx, if that was our problem, that ends up being actually a lot harder to deal with than the one we have, even though the one we have looks more complicated. And we won't have to deal with that in this class. All right, so let's take a look at this one here. Do we see something whose derivative appears somewhere else? Well, the derivative of x squared is 2x. So I think I might have x squared. Now, the issue is, if I pick u equals x squared, then when I get du, let me just run through this. This is not the correct choice of u. But I go through and I get dx equals du over 2x. And so I would get 2x u plus 3 to the 4th du over 2x. So those cancel, and I end up right here. The only problem is I don't know what the antiderivative of u to the u plus 3 to the 4th is. Instead, if I had gotten u to the 4th du, I know what that antiderivative is. I can use the power rule. It's u to the 5 over 5. So maybe let's go back to the drawing board and see if we let u be that whole thing in the set of parentheses. So if I let u equal x squared plus 3, well, what's the derivative of that? Oh, it's still 2x. So if I solve for, I went through that pretty quickly, so let me add an extra step here. So if I solve for dx, so multiply both sides by dx, divide by 2x. Now it's going to work out a lot nicer. So I'm going to get equals the integral of 2x, and x squared plus 3 is u, so I get u to the 4th. dx is du over 2x, so du over 2x. Well, what do you know? Cancel, cancel. I get integral of u to the 4th du, which the antiderivative of that is u to the 5th over 5 plus c. And then I substitute back in, so I get x squared plus 3 to the 5th over 5 plus c. Now notice b, again, they look very different, but I have a function times a function to the 4th. A function times a function to the 4th. So I'm going to let u equals sine of x. Then du dx is equal to cosine of x. And so du is equal to cosine of x dx. And I get dx equals du over cosine of x. So again, I'm running through that step pretty quick. I just take the derivative, multiply by dx, divide by cosine of x. So now, first things, before I start substituting, let me rewrite this. A lot of times people get a little confused. Don't forget sine to the fourth of x really means sine of x to the fourth, like that. So I'm going to have integral of cosine of x. Sine of x was my u, so I'm going to have u to the fourth. And then dx is du. Again, I'm substituting this guy. So I use this guy above, right there. I'm using this guy down here. Cosine of x and cosine of x cancel. So I get integral of u to the fourth du. The antiderivative of that is u to the fifth over 5 plus c. Plug in what my u is. I get sine of the fifth of x over 5 plus c. So really, when you're watching this, try and take a moment, maybe pause the video, and make sure you see the similarities between A and B. Even though they don't look very similar, look for the similarities, and once you start to see them, everything becomes quite a bit easier. All right, so example 3, 2x over x squared plus 3. Again, do I see something where its derivative appears somewhere else? Well, if I let u equal the bottom here, then du dx, the derivative of that is 2x. So I get du equals 2x dx. And then I get dx equals du over 2x. Well, let's see what happens if we do that. So I've got 2x on there. X squared plus 3 is my u, so I'm using this guy. Now let's use this guy. Dx is equal to du over 2x. Oh, well, 2x and 2x cancel. So I've got 1 over u du. What's the antiderivative of 1 over u? Remember, that's the unique one. That's ln of u plus c. So I get ln of x squared plus 3 plus c. And I dropped the absolute value bars because x squared plus 3 is always positive, but you could have absolute value bars, so that'd be fine. All right, now B looks nothing like A, but let's see if we can figure out how to do it. It actually is very similar to A once we see it. So what's the definition of cotangent? The definition of cotangent is cosine of x over sine of x. And now, if we let u equal sine of x, well, the derivative of that is cosine of x. So I'm going to have I have a function and its derivative appear somewhere. So I think I'm on the right track. So du dx equals cosine of x. Du equals cosine of x dx. So divide by cosine of x, I get dx equals du over cosine of x. So I'm going to have cosine of x, doesn't change that, over sine of x is u, so I'm using that top one here, times dx is du over cosine of x. The cosine of x's cancel, so I get 1 over u. Make sure this u doesn't magically move up. A lot of times people cancel there and it just turns into u du, but don't forget it's still in the denominator. So 1 over u du, the antiderivative of that is ln of u plus c, and u is sine of x, so ln of absolute value of sine of x plus c. Is our answer. All right, so let's just keep going. Why don't you take a moment before I tell you, think what you might choose for your value of u. All right, so we're looking for a function and its derivative. Notice the derivative of z cubed is 3z squared. I don't have 3z squared, but again, I can be off by a constant. The key is that the derivative of z cubed has a z squared in it, and I have a z squared up there. So I'm going to let u equal z cubed plus 1. Then du dz equals 3z, I wrote an x, 3z squared. Du equals 3z squared dz. If I solve this guy for dz, I get du over 3z squared. Now let's substitute. So I got a lot of room over here, so let's bring it over. I'm going to have z squared over u, that's using this guy right here, and then replace dz by du over 3z squared. The z squareds cancel, so I end up with 1 over 3 u du. Now, some people might get a little confused by this, but don't forget we can pull out a constant out in front. So I can rewrite this as 1/3 1 over u du. And now this is a pretty familiar antiderivative. It's 1/3 ln of u plus c. So I get 1/3, finally I have to substitute back in for u, so 1/3 ln of z cubed plus 1 plus c. All right, so the last two are trickier. Now again, I'm not saying the ones before are easy, but as far as a u-substitution, they're pretty straightforward. These ones get to the point where they're not quite as straightforward. All right, so notice, if I try to pick u equals 1 plus x to the 4th on this one, then du dx is going to equal 4x cubed. Well, I have an x there. I don't have an x cubed. So actually, let's just run. This is incorrect, but let me run through this and show you what happens. Because sometimes people try to make it work anyways, but it's just not going to. So let's multiply both sides by dx. And then let's divide by 4x cubed. So when I do this, I get x over u. That's using this guy here. And then I get, substituting for dx, I get du over 4x cubed. So when I do that, notice x, and that becomes this x squared, but I get du over 4x squared u. Right, this is a u and that's a 4. All right, so when I do this, I have x's and u's. If I get to a point where I still have my old x's in there and I can't figure out a way to get rid of it, I cannot just, there's no way to integrate this as it is. So make sure, notice in all these other cases, we started with z's, we did our substitution, all the z's canceled. Here we started with x's, we did our substitution, all the x's canceled. Right? Just keep that in mind. On all of these, all the original variables canceled. So I started with x's and I ended up entirely in u's. This one, I started in x's and ended up with u's and x's. That is not allowed. There's no way forward from that. I need to get everything to a u. So I need to get rid of all the x's. So that's why I said, like I said, this one's quite a bit tougher than the other ones because the choice of u is not obvious. But what has derivative with just an x in it? Well, x squared does. So let's see what happens if we let u equal x squared. Then du dx is equal to 2x. Then du is equal to 2x dx. Divide by 2x and we get du over 2x equals dx. All right, so we're using that guy. We're going to use that guy. So I have x over. Now, x to the 4th is x squared squared. So I can, if I replace x squared by u, I'm gonna get, or x to the, yeah, if I substitute in x squared for u, this becomes a u squared, right? Because x squared squared gets me x to the 4th. Now dx is 2u, or sorry, not 2u, du over 2x. All right, so the x's cancel. Oh, great. Now we're down to all u's. That's all that I needed to happen. So now I can rewrite this. This is 1 over 1 plus u squared times 2 times du. So what I like to do is write that 1/2, that 2, pull that 2 out in front, but it's on the denominator, so it's a 1/2. So I like to write it this way. 1 plus u squared du. What's the antiderivative of 1 over 1 plus u squared? That's part of the reason why it's tough, is you might not have recognized that that is arctan, right? 1 over 1 plus x squared is arctan, so this is arctan of u plus c. And now, substitute back in for u, I get 1/2 arctan of x squared plus c. And that's my answer. Like I said, that one's a tough one. And finally, there aren't very many that you have to do this. And, you know, come test time, if it's at home, well, then the test might be open book or something like that, and there might be something like this. But if it was at school, or if it's proctored at home, this last one might be a little too difficult for a test. But I think it's useful to know. I have it on your homework, so it's kind of a homework only level of difficulty. So looking at this, I don't have a nice obvious choice of u. The only thing that I can see is if I could somehow get this to be u to the 6th, it might be nice. The only problem is, what's the derivative of 2x minus 3? It's just 2, so I'm not going to get rid of that x. Well, let's see if we can get around that. So 2x minus 3 for our u, then du dx is equal to, the derivative of that is 2. So du equals 2 dx, and du over 2 is equal to dx. All right, so we're going to use this guy. All right, so I get integral of x times u to the 6th times du over 2. Now remember, the first time we did number 5, we did it the wrong way, and we ended up with x's and u's, and I said there was nothing to be done there. In this one, I might be able to do something. Because notice, I have this guy here. I could write that as u plus 3 equals 2x. So u plus 3 over 2 is equal to x. We're going to have to use this guy as well. So if I substitute that in, now I've got u plus 3 over 2 times u to the 6th times du over 2. Well, now I have all u's. I've gotten rid of all my x's. It still looks not very pretty, but notice 2 times 2 on the bottom gets me to 4. Let's write that out in front, 1/4. If I write it this way, now all of a sudden it's starting to look a lot better, because I can distribute that guy through and get u to the 7th plus 3u to the 6th. That's a u. So I get 1/4 u to the 7th. The antiderivative of that is u to the 8th over 8 plus 3u to the 6th. The antiderivative of that is 3u to the 7th over 7 plus c. And so let's substitute back in for u. So I get 2x minus 3. So, and I'm going to multiply through like that as well. So I get 2x minus 3 to the 8th. Let me write that a little bit neater here. 2x minus 3 to the 8th over 4 times 8, which is 32, plus 3 times 2x minus 3 to the 7th over 4 times 7, which is 28, plus c. Make that c a little bit clearer, that that's a c. And that's our answer. So that is one of the toughest ones that you'll encounter in this section. But you'll notice you have plenty of time to work on this section. I actually split it into 4 separate days worth of work, with one of the days just, well, 5, really 4, because I did one of them for you. 4 questions, where, again, make sure you look at the hint. 46 through 48 are very similar to what I did in example 6. So as usual, let me know if you have questions, and that is it for this section.